Thanks for coming, everybody. My name's Fritz Klassner. I'm with the Office of Maunakea Management. This is another installment of our Maunakea Speaker Series, basically a monthly presentation on some of the work that's done scholarship on Mauna Kea. It's a partnership with UH-ELO, Department of Physics and Astronomy, the ELO Astronomy Center, and our office, the Office of Maunakea Management. We're actually fortunate in that in May we have two presentations. The next one is May 31st. Nathan Stevenson, who is a recent TCBS master's degree student, will be talking on the 31st in this room on arthropod habitat mapping on Mauna Kea using LiDAR and some of the remote sensing data that he did for his master's thesis. So yeah, there's another one here coming up in just over 2 weeks. But today we are particularly fortunate in that Dr. Jane Ellen Massey, as she was known when she did her research back in the 70s. Now Jane Massey Licata is a professor at Rutgers University and a partner in a law firm specializing on biotechnology and patents. I'm going to not try and introduce too much more, let you get it more accurately characterized than that, but she did her doctoral thesis with the University of Hawaii at Manoa back in the late 70s, looking at diatoms and sediments in Lake Waiau, working with some names that I think many are familiar with. Dr. Alfred Woodcock was one, who is working up on the lake. Siegel was your maybe?
Sanford Siegel, John Michelik, Joyce on my committee, yeah. So
a number of well-known but now retired, and some have unfortunately passed away, professors from University of Hawaii at Manoa. But Dr. Licata is here visiting with family and graciously offered to share some of her insights about her research on Lake Waiau from her doctoral thesis. And we're very fortunate today to have the opportunity to go out to the lake with her, talk a little bit more about her research and learn a little bit more. And with that, just want to say thank you very much. She has a few slides to show, and so the photos from before were actually her photos from back in the 70s when she was doing her work. And with that, Dr. Licata, thank you very much.
Thank you, Fritz. Well, welcome. I mentioned to Fritz this morning that the last time I talked about Lake Waiau, there were 6 of us in the room. There was me and my 5 committee members for my dissertation defense. And there was only 2 of us left standing. So it was really quite wonderful. My wish was really to come back and visit Lake Waiau, and I wanted my son, my youngest son, to come with me because when I was 21 years old, I spent my birthday on that lake. I worked up there for 3 years for pretty much every month over that period of time. And when you're a parent and you get to this point in your life where you want to share and explain some things that were very significant moments in your life. And for me, Lake Waiau was a point and place of beginning. It was where I learned to really be a scientist and how I learned how important it was to ask questions, to seek answers, to not always get the answer that you expected, but that everything was part of what ultimately would become a bigger picture of your life. So for me, it was coming back and being able to share that with my son. And then it turned into quite a bit more because I realized that many of the things that have been questioned I had asked or people had asked me about Lake Waiau were still relevant questions and things that people were interested in. And in the discussions that we've been having, I thought this would be a nice opportunity because I'm in my 60s now. So if I can share with you, perhaps people will remember and know some things about the lake that perhaps aren't commonly known. Because beyond my dissertation, I published several papers, and they are still cited, interestingly, mostly because I discovered a new species of diatom up there, which we'll talk about. And that in Hawaii, this has happened a number of times where new species have been discovered and named and continued to be relevant, but it hasn't happened that often. So we'll talk about the little Starineus Maunakea and what that diatom has to tell us about the history of Lake Waiau spanning a period of 30,000 years and what it tells us today about Lake Waiau. This was a picture taken back in about 1976. I worked on the lake from 75 through 78. It was really wonderful to be able to go up there quite a bit. Back in the day, though, I mean, there were no personal computers, there were no cell phones, and I had a very good friend who ultimately had a career with the U.S. Fish and Wildlife Service. She was a plant biologist. So we would work 10 days over on her project in Volcano National Park and then go 10 days up Lake Waiau. So we were both doing research and helping each other over this period of time. And we have continued to be lifetime friends because of that. But we basically would fly over from UH Manila, pick up the little Toyota Land Cruiser that you saw in some of the pictures at the beginning, and we would vanish for about 20, 21 days every month for 3 years. So it was a very interesting time, and a time when, because we were over here quite frequently, we got to see the environments we were studying throughout the year, and as conditions changed from year to year, which we became very familiar with what the environment really was like. So this was Lake Waiau back in the day. This is one of the years when it was really quite full. And it was a very wet year. There was a lot of snowfall that year. And it was really quite beautiful at that time. There's some unique aspects of the lake, and this is what started the inquiry. My major professor, when I was talking with him about a project, had a question in his mind. And Dr. Siegel was an organic chemist, but he was very interested in extreme environment ecology, and he was particularly interested in the effects of heavy metals on life. He believed that chemistry was life, and he was very interested in, if you had, particularly he was interested in mercury and some other of the heavy metals. And he was very interested if you were in an environment where perhaps those levels would be higher than normal, and you had to define what normal was for the type of environment, that perhaps you would see a biological impact. So the question was, he said, I heard that there's this lake up in Maunakea, and since there's a lot of volcanic activity, I'm curious if there's maybe extremely high levels of mercury that might have an impact on the lake. You should go up and look at it. Before you go up and look at it, you should talk to Professor John Michelli was at UH, and he'd been up there a couple of times. He was interested in collecting insects, and he had collected a couple, but he wasn't much interested with what was in the water. But he gave his observations, and then they sent me over to see Dr. Woodcock, who had taken core samples down to about 7.5 meters, which spanned a period of about 30,000 years. And he was kind enough to tell me about his work and to allow me to evaluate the geochemistry of the sediments and the carbon dating, so I could understand over a period of time what had been going on in the lake. So I talked to these gentlemen and then went up to the lake to see if I could actually manage to work over there. They both had been up there several times, but thought that, in fact, Dr. Woodcock said to me, you'll probably die up there. He just couldn't imagine. At the time, I was like 20 years old, and he said, you're not going to make it. But I thought, okay, well, let me go and see. Well, I went up to Lake Waiau, and it was really an interesting visit. And I thought, I can go up here, I can work, so let me try to answer some of these questions. So I did sample the water and get the lay of the land with the lake. And in doing that and then studying the sediments that Dr. Woodcock had initially sampled from the Bonneville Lake, was be able to start the beginning of the story to understand what was special and unique about Lake Waiau, and what was going on in this lake, and what could it tell us about how the organisms in the lake were responding to the environmental conditions. And there were a couple of things that were very unique about Lake Waiau. It is not the only tropical alpine lake in the world, but what you'll find in tropical alpine lakes is that usually they're very isolated and they have fairly extreme conditions in terms of highlight and temperature and so forth, so that you're looking at a situation where the ecosystem is going to be very simple. And therefore, it's a little bit easier to figure out what is going on and controlling the life in the lake. So I knew it was isolated. I knew that there was highlight intensity that was going to impact what was going on there from a biochemical situation. And one of the things that he had asked me was, do you think, what heavy metals are up there, and do you think that that is having an impact on what's happening in the lake? And because of the geology of Hawaii, like many other areas where there's been volcanic activity, it's not unusual to find heavy metals in the sediments. And in fact, there were relatively high levels of copper, zinc, and nickel. And when you look at other lakes which had a similar history, these are not off the chart levels. They're consistent with that type of geologic history. But when you have high levels of the heavy metals, it will have an impact on what life can survive in that environment and how it will behave. The other thing that's kind of interesting is, I don't know if you've ever seen pictures of Lake Waiau or been up there, is that the lake sometimes appears beautifully blue, and sometimes it has a real green cast to it. And the reason that is that there's some different types of algae in there, and there's phytoplankton. And then what I was interested in was the diatoms, and I'll explain to you why. But what actually was happening in the system and controlling the dynamics of the population was that it was actually the sulfate levels were of such that it was sulfate limited. So it was necessary for a certain levels of sulfate to be there to really bring the population to its full potential. But this was a factor which was often limiting. So we did have high levels of particularly nickel, and we had sulfate limitation. We had extreme highlight intensity. Basically, the productive zone of the lake was about 1.5 meters down because of the highlight. And what happened as a result of it is that for the species of the diatoms, which I was using as biomarkers, I could track over periods of thousands of years where those levels were, how they had changed, and how the population had evolved and changed with it and adapted to it over time. So this is, I'm not going to bore you with all of the tables, but what I was looking for was how productive was the system was one of the factors. Is what was going on in terms of the photosynthesis. The diatoms are single cell plants. They're very unique in that the cell wall is made of silica. Now the great thing about that is it can protect the organism under some extreme conditions, but also when the organism dies, it becomes part of the sediment. So the beauty of it is that you had the chemistry of the organism which allowed it to survive and adapt in a challenging environment. And then it became part of the record where I could correlate it with the conditions in the lake and figure out what had happened over thousands of years, depending upon what the conditions in the lake were. So what I had done is gone through a growing season and followed what was happening from a biochemistry standpoint, population dynamics, how what the character of the diatom population was and how it changed over time. And then also looking at, in terms of the light and other factors, what happened over the season. Generally what happens at Waiau is that there will be a bloom, and it usually occurs in summer, and you'll see a buildup of the population. So it builds from over the summer, so that August is usually when you'll have the most intense populations of the diatom species. So this is all done pretty old school, because this was, again, before computers and before cell phones, before a lot of equipment was small scale and easily portable. One thing that we were able to do that is different to today was, at that time, you could drive down to the lake. And frankly, if we hadn't been able to do that, we would have never been able to take in all of the equipment and do everything that we had to do. But there weren't very many people. I was a little surprised today as how much traffic there was, but the road wasn't paved like it is today, and there wasn't as much going on up there. And I also think a lot of people didn't know about it, so it was very quiet. And at that time, as long as you had a good reason, I was permitted under a research, because the research was supported by natural resources, by University of Hawaii, by the Pacific Tropical Botanical Garden. So there was a reason and a reasonable scope of plan to work there, and I was allowed in and with the UH vehicle. And so we were able to do this, and what we had done is I set up a transect. When we go up, we would put outline, put the rope across. We had a small little boat, and we did a whole bunch of series of experiments going down from surface half a meter down to 2 meters. We tested the water, characteristics of the water, the buildup of the population, the decrease of the population over throughout the year, and tried to figure out what factors were most important in controlling the nature and character of the population and how productive it was over the course of 3 years. Now, this was something that was very unexpected. When I looked at the sediments and I looked at the contemporary sediments and water samples, I found this little tiny diatom. And I first saw it on a microscope slide, but then I ended up, it was quite wonderful. I was able to study all the sediments and the contemporary population with electron microscopy, which is pretty new at the time, but it was great because it really gave me the opportunity to look and be careful on identification and understanding what these little diatoms look like, because you can't see them with your naked eye. Now, all of the references for these diatoms were based upon the visual microscopic identification. So when you find something that isn't matching up with what people had seen before, and then you're confirming it with a new technology, the question is are you looking at something that it hadn't been possible to see before, or is it truly something different? And there was nothing in any of the literature, and I talked to some people that were very knowledgeable about diatoms all around the world, and we came to the conclusion that this was something quite different. It was tiny for this genus of diatom. It was remarkably small. It had a much denser laydown of the silicon, and the pattern was quite distinct. And all of these things indicated that you had an organism that had adapted to this unusual environment. So it was able to tolerate the high light intensity. It was able to adapt to the chemistry of the environment. And some of the other diatoms that are there are about a dozen species that are up there, have become adapted to the environment. So they look different or they have things about them that are different to what a more typical example of the diatom would be. But they had moved to the level of something completely different, a new species. And of the about 12 species that you would find in the contemporary population and in the sediments cores that we were studying, we found that there were some of them we call cosmopolitan species. There's stuff that is commonly in Hawaii. How the diatoms got up there generally was they come down in the rain, because that's how the lake gets its water. It's from the rainfall and then the snow melt. So it had to be something that came in and down into the lake. So there's some species that are found in Hawaii. They got up into Waiau's environment and they adapted to the harsher conditions, but you looked at it and you said, that's a bat. And over time, if you look at the cores over thousands of years, you would see that they had become maybe changed in size or the density of the silica or whatever, but they were still something that was within identifiable characteristics of the species. But not this little guy. He was something quite different. And this was found all the way down, so for at least 30,000 years, this had become a unique species. Now, the interesting thing about it was after you come up with a new species, you get to name it. And there's several different conventions of how you would name it. You can name it after a person. Sometimes people do that to honor a person. The Dr. Siegel told me if I did that, I would not get my PhD. He was a very humble man. The other thing, sometimes you name the new species because of certain characteristics that it has. And another thing you can do is you can name it after a place. It seemed to me that naming it after Maunakea said a lot. I could say very little, but say quite a bit. It placed it as this lake, that had an association with a mountain. So it suggested that it was a unique environment. It spoke to Hawaii and the fact that it was something that was endemic and unique here. And it spoke to the deep history of the mountain. So to me, it seemed like a perfect name. You have to name it in Latin, so Maunakea became Maunakeensis. And then the next challenge was, thank God I had 4 years of Latin in high school, is you have to write the species description in Latin. And then you have to send it off to 2 independent sources where they have a collection and an expertise to determine if you're correct. So samples were sent to the British Museum and to the Academy of Natural Sciences in Philadelphia. The British Museum confirmed it, and then Dr. Ruth Patrick, who was at the Academy of Natural Sciences in Philadelphia, confirmed it and offered me a postdoc because she was fascinated by this little diatom. And one of the reasons she was fascinated is Dr. Ruth Patrick was a pioneer. She had found that diatom populations can tell us a lot about the health and the history of an ecosystem. They're actually used as biomarkers to show if the system is polluted, if it's improving. And she had pioneered this in lakes and other aquatic environments all over the US and ultimately the world. So to her, diatoms told us so much, and such little things could be so informative, and let us not only know what an environment was like that could have created this unique species, but it also allowed us to look over periods of time and see how the environment had changed. So we were trying to understand why this stardiness had adapted in a particular way, but we also wanted to understand what had happened at a point in time that had driven it to adapt. Now, the cores that we have are only down to 7.5 meters, so I can only tell you that at some point, more than 30,000 years ago, I didn't know exactly at what point. But I can also see some other things from the numbers of these diatoms and how it correlated with the levels of certain elements and other things that you could see in the cores. For example, if there's volcanic eruption, it was visual. The cores are quite beautiful. there would be different colors, different spacings between the striations, but you could look down and you could see where things would go along season to season or decade to decade or century to century. And then there were some very unusual things that happened at certain points in the core, which I wanted to understand what those things were. And star anneas, the population would rise and fall, and you could correlate to some extent some of the things that were going on from the record that was left in the sediment. There was one that was really interesting, is that at one point in time, about 1,000 years ago, in addition to the little star anneas, there was a couple of other species, which these cosmopolitan species, that came into large number. And so I was curious what had happened at, around 1000 AD that had caused this change where there was much more diversity in the system. And although star anneas was there and sort of constant, these other two new species, not new in the sense of as new species, but something had been at such a level at Waiau before, was there. And so when I started talking to people, I said, what could have happened on the mountain? I'm not seeing it in the core, really, except to see the change in the Diatom population. Do you know of something that happened about that time? And it was pointed out to me that there had been an axe quarry. And Waiau was believed to be the fresh water source for the workers. So again, when the humans came in, and they could have been using things to collect the water, or spending more time at the lake, or had actually brought in large numbers of things that were normally found down at sea level. And they came up with the people that came into the lake. The lake had to adjust to that. But over time, those populations of things moderated down. They did adapt to the lake somewhat, but things went back to more of the steady state, and Waiau became more as it had been before after it made that adjustment. Now those species are still up there, and they are unchanged. They're the same characteristic as the ones that are found down at sea level. But it was interesting because that was the first time you saw the hand of man that possibly was coming in and changing things. It wasn't the rain anymore. It wasn't the dynamics of the water chemistry or a volcanic event or more or less rain. It was something very different that had happened. So one of the things if you want to assess the change in the lake ecosystem, any lake ecosystem, the geochemistry can be very helpful. And again, because I was very fortunate that I had these sediments and I also had all of these contemporary measurements, I was able over a period of time to understand the elemental composition, to figure out which factors were most important. And I also had searched the literature for other similarly placed lakes with a similar geochemistry and history, and found an understanding of what was going on. And the bottom line was that over time, and even today, that there's a couple of driving factors, but it's mainly the physical environment and the reflection of the volcanic history of the lake sediments that affect what's going on up there. What was also kind of interesting is that we did have an opportunity to do a more recent, when I was up there toward the end, quite a more extensive collection and evaluation of the contemporary sediments. And that's something that, in understanding, like I said, the color of the lake, what was going on. And the way I kind of explained it simply today was, if you build a swimming pool and you paint the bottom of the pool blue, then the water looks very blue. And if you painted it green, then the pool would look green, so that the light reflects that. What's on the sediments is the mats of some of these other blue-green algae and so forth, which lend the color. So when they go through their bloom, that the color will appear to be more green than blue. But today it was a bit more green. And but when I put the water up and you looked at it, the water was absolutely clear. So it's not something that's in the first 1.5 meters of the water that's causing that. It's really a reflection of what is down on the sediments. Because I never ever saw up there. It's not only kind of out of the blooms, like you'll see things floating, you'll see bubbles and stuff like that. This has always been something more at the sediment rate, at the layer. Yes?
What depth are these sediments at?
It depends. Most of the time when I was up there, it was maybe about 8 feet deep. The most I ever saw was 12 foot. If the lake is about 12 foot deep, then you're going to get that, you'll get some overflow through the gulch there. I've seen the more recent aerials at one point where it actually got quite small. For the diatoms, that's not a problem. And even historically, you can look at the sediments and see there were periods when the lake was much smaller, apparently, because the populations went down. But a diatom, if it's moist, if the sediment's moist, it can survive. It's not dependent so much on the water column. And because of the photo inhibition, the light intensity, most of the productive levels is occurring about 1.5 meters. So that's really, so as long as you've got about 6 feet of water in there, the lake is balanced, and at least the diatine population is efficient. When the water level is lower and that productive level is pushed closer to the sediment, you'll see the production go down, because in that sediment are some of those things which challenge the species normally. So that 2 meter interface with the sediments, that's when the nickel levels and the sulfate limitation tend to come into play, and they can accommodate as well. They don't die, but you'll see a decline in the population because it's not as efficient. And to me, it ended up, the chemistry, I love chemistry. I ultimately became a biochemist. The biological markers, these little diatoms, could tell us so much because they were so strongly influenced by just 1 or 2 factors. And so the biological markers, and in terms of the number of species, the species that clustered and occurred together, over time, over particularly a 5,000 to 6,000 year period of time, and compared to contemporary, was very helpful. And you saw the same pattern over and over again. So this system actually is quite remarkable. It's very elegant. This group of organisms that are in there have been able to adapt and adjust, and as long as things stay within a pretty reasonable zone, which seems to be the natural condition for the lake, it endures. Thousands of years it's endured. And the organisms that are there are able to adjust to the situation, but they're also able to speak to us over thousands of years because a record is left of what they were made of, what the environment surrounding them was, and what other organisms were associated with them in such a way that you can understand from year to year, from century to century, what was going on. So the question at the time that I did this study was in part, there was discussion of did there need to be a management plan for Lake Waiau, because Waiau is a very special place, and it's special in Hawaii. It's, you have this lake sitting up on top of this mountain. It has a very significant cultural history. It's a sacred place, and it's something that can also tell us
what's happening on the Big Island, what's happening on Mauna Kea, to some extent, because we can understand how these little biomarkers are behaving and why. So what can it tell us about the past, the present, and future? We can tell us that Lake Waiau, over about 30,000 years, has within, except for the, it has been pretty much the same. Okay, it varies in size sometimes, but in terms of a core group of organisms, a fundamental geochemistry, and a level of productivity, it's not like there's been anything so terribly dramatic that we put a finger on it and say this is the end of Lake Waiau. It's pretty consistent, and it's over time has been able to sustain itself in that fashion. At one point, and I know it's funny now because the folks at UH and the Maunakea Management Group were very kind to share with me all these wonderful aerial photos of the lake. Well, back in the day, I actually found a guide that flew for the Civil Air Corps, and I said, I really want to see what it looks like from the air. He says, come on. And we went up and we took this picture of Waiau. And this is one of the periods, one in between from year to year, where it was a little drier, and you can see where the lake wasn't filling up the heart shape. But then the next year, which is the picture at the beginning, it was almost overflowing into the gulch. But we also had been able, because we were able to get down and be consistently measuring certain aspects of the lake, sort of mapping the depths and the bottom of the lake over the time as well to see how it changed. There was actually a report at one point where somebody had, I think it was back in the early 1900s, that had spoken of Waiau and even said it was a bottomless lake. I think what they might have done is just hit the sediments, because the first bit of them, the first meter, aren't compacted, they're squishy. So if there was a bloom in the lake and you couldn't see down, you might get a misimpression, perhaps it was deeper than it was. Because it really is sitting in the cone, and it does have a deeper point, but again, it had been pretty consistent, and there's a consistent layer of sediment there.
Oops. Okay. Oops. I think, yeah. That's right. That's sort of the end of the slides. I think that one of the things that impressed me this morning, so much about Lake Waiau, I hadn't been up there since 1978. So that's like almost 40 years ago. And when I came down into the lake, it was like a familiar friend. It was looking very good. It was looking very much as I had always known it to be. And, I didn't bring in all the scientific equipment, but, just some of the quick things of, looking at the turbidity and looking at what was on the surface and so forth. It was very comforting because over a 40-year period of time, and there's some places you go back to that are dramatically different, and the lake wasn't. So that was very reassuring to me. Part of me is I would love to have checked to make sure my old friend Staranius Maunakea was there, but I'm pretty sure that it is. And it's the kind of thing that, because I had come to know and understand the lake over tens of thousands of years, that I'm pretty sure that if I had repeated and had the opportunity to repeat some of these measurements, that it would be within the historical context of what made this lake work and continues to make this lake work. So I do thank you all for allowing me to come up today and visit an old friend. I'm trying to talk to another UH student maybe picking up, and she would have an easier time of it. I mean, and this is looking back on it.
one of the things, it was really hard to work up there. It was so hard. I remember that as I was hiking out, like, because you can't drive down there anymore. I'm a lot older, but I'm not in terrible shape. And it was like, you know, it would be very hard to work up there for 10 days. And it'd be hard to work up there in the cold. And it'd be hard to be standing out. We had bottles down and we're running assays from 10 in the morning till 6 at night, day after day after day. And then taking all these other measurements and so forth. And it was just, it's dozens and dozens of experiments done over the period of the 10 days. And then when times were different, we load up our 60-gallon ice chests, we drive them to the airport, and we fly back. I mean, I would never have been able to do that now. But it was, looking back on it, it was patient kind of old school field work there, and then coming back to UH. At the time, it was very high-tech stuff too, because I was using an electron microscope, and then I was analyzing and carbon dating all of the sediment and all of the samples, sort of to create this matrix of all the variables that could come into play. And then you had to statistically analyze them to match it up with what you were seeing in your results to try to figure out, okay, what was driving the system. And fortunately, because it is a relatively uncomplicated system, a very elegant system, you know, being able to figure that out. So I think that you know where you would start, and in terms of, I think you would find that hopefully it in fact, as it appears today visually, a remarkable place, birthplace of a new species, something quite wonderful as a resource for our lake. It teaches about culture, our history, both scientifically and biologically as well. And it was, for me, a point and place of beginning, because once I learned that it's, you know, how to ask a question, how to try to answer it, how to kind of adapt my thinking when things weren't quite the answer that I expected, that it was okay to fail, but sometimes you learn more from it not going right or having to find another way to solve the problem. And then from that point, everything else that happened in my life was a build on that. Because I went from this study to my postdoc with Ruth Patrick, who then got me a job with the Environmental Protection Agency as a water quality expert with expertise in heavy metals and the impact on an ecosystem. And then from there, because I was working a lot of cases as an expert witness, I ended up going to law school, and then I became an environmental lawyer. And then I expanded out into other parts of the federal code of regulations. So now I represent about 30 or 40 universities in the US and abroad, and I help them create research opportunities to take technology and basic research and to take it to another level where it can, particularly in the biomedical field with a lot of natural products chemistry, come up with new therapeutics and so forth. So every step along the way was learning the lesson of Waiau. Be patient. Ask a question. Try to find the answer. See where that will take you. Take a chance. And and so the University of Hawaii was very good for me. It gave me chances and choices. It gave me opportunities in life, and it gave me the opportunity to keep asking questions and to sometimes fail and to learn from that failure, and to also learn that if you work hard, you can dream big, that you can accomplish something. And the fact that we're here 40 years later and people are still interested in Lake Waiau because you love it as much as I do, is just quite wonderful. So thank you for your time and attention. And if you have any questions, we can talk more science, whatever. Yes.
In looking at the cores, can you distinguish different sediment rates, sedimentation rates based on full glacial situation, which was the present 30,000 years ago, and deglaciation of Maunakea in the last 10 or 15,000 years? I mean, was Lake Waiau frozen over completely and therefore low sedimentation during full glacial, or what was going on in this lake?
Well, you know, I talked to Dr. Woodcock because he was very interested in that question. And in terms of the different rates of sedimentation, I mean, there were visuals, and with that, I think in terms of whether the lake was completely frozen over at that point, I'm not sure. But if you look at the older settlements and the differences in the striations and so forth, and you know, the colors and the character, it looked back at that point in time whether the system might have been, the striations was still there. It was in low numbers, but it was present. So it wasn't like the lake had become completely dormant and everything had died off. So that was the interesting thing, that at least at that point in time, there was still the population that was there and a clear, you know, it was laid down in the sediment. So there wasn't like this void where it was frozen and lifeless.
So you see interannual larves in the lake?
Well, it was, you could see, as Dr. Woodcock is saying, you could look at periods of time. So you're not looking at year to year like I was in the contemporary stuff. But you could see, you could look at a section and we would date it and within 500 to 1,000 years during that period of time, you could look at it and determine whether the lake was in fact active. So there was an active population, and there was what was happening in the geochemistry was a consistent thing, at least at that point in time. And I would love to have gone back, and I just found out that they don't have the course anymore. They were lost. Because I would, you know, at this point, I would love to have gone back and looked at that, because I know there are more questions, but to get the course is really difficult. You know, if a couple of people that have done it up there, and Dr. Woodcock was generous in that if you were interested with his supervision, you know, he would let you work at it. And he took it a different perspective because, you know, he was a geologist, and where I would come in and I was very interested in carbon dating, understanding the timing, and I was very key understanding what diatom populations were there and correlating that with the analysis of the geochemistry. He was a little more focused on slightly different things, but it wasn't, you know, maybe it was below that period, but at the point where I started looking at it and then moving out, particularly the last 5,000 to 6,000 years, of course, that's more contemporary history. The lake was very active.
Are there still plankton in the lake?
Yes, I'm sure there are. I mean, well,
Which ones?
yeah. Well, I can tell you that over thousands and thousands of years, there were only about a dozen diatom species up there, and 8 of the 12 were consistently present in the sediment and in the current environment. So it's been very consistent over a very long period of time. Like I said, when I took the vial of water today and looked at it, it was very characteristic of the thousands of waters example. I mean, it was a long time ago, but I don't think my memory's gone that bad. So that was something I really would love to have done today too, but, you know, just bring it back and do a quick checkup on it. But I'm hoping maybe there'll be a young scientist, and I would love to work with them. Yes.
With the data you collected, could you tell how many distinct periods of low water level there was?
Well, you know, it's funny. One of the questions I was asked is did I recollect that, or did I ever see where the lake went dry, or that they showed me the pictures of the 2010 when the drought had occurred, and if the lake levels did fluctuate because it is precipitation dependent. There was not anything that I looked at in where everything just crashed and died. There was always, it was just a question of how many species, how many individuals of that species, and what kind of geochemistry they were sitting in context. So for sure the last 5,000 to 6,000 years, there was nothing that said the lake went dry. And now, if you go and look at it today, it's like, to me, it looked just like it did in the 70s. So I think that the lake is, the environment, the populations, at least diatoms, are very tolerant because they just need moisture. So if the sediments are moist, and they really are, even when the lake was dry, Chris had told me he had looked at the bed, and it wasn't a biological desert, and of course it did recover. But if you compare, like I said, if you look at the humidity of the water, you look at, it was blooming, it started its green phase. I would never have known that the lake could become that small if I hadn't been shown a picture of it. I would have, based on everything I'd seen over thousands of years, thought, it was the same.
Follow-up question.
Yeah.
Did you do any studies with nitrogen, presence of nitrogen in the water?
Yeah, because that was one of the things that we found the sulfate limitation, but one of the questions was there something going on there? And from that standpoint, there was nothing that was unexpected, and it certainly was not a factor that was driving the population. It wasn't limiting it, and it wasn't causing it to explode in a particular fashion. It really was the sulfate was the dynamic. Yes.
How did lake form? You say it was in a cinder cone?
Yeah, it's in the cinder cone, and there's more recent research that was brought to my attention. Back when I was working on Waiau, and based on all the historical documents I read back into the 1800s, where we had people talking about visiting the lake and so forth, it definitely has to do with the sediment layer there, which is allowing the lake to continue and just have so it's not porous, it's not draining. The theory when I was studying it is that they thought there was a permafrost layer there that was also allowing the lake to exist. My understanding is that from some more recent studies, they don't think that's like it's really much more the sediments, the way they're packed, is what allows that lake basically to be a sealed enough bowl that it basically holds the water, the annual precipitation. I think he basically said that the thinking is not that there is a permafrost layer anymore.
Yeah, there might have been in geologic time. There probably was when it was glaciated, but in any sort of meaningful recent history, there's no meaningful permafrost.
Yeah, and I think that a lot more is known now about that area, and from the ice. The ice issue is something, and there's much more sophisticated technology than a guess on that now, in terms of ground penetrating radar have been used, and also we're into like the age of computer modeling and all of this stuff as well. I mean, the modeling that I was doing was based on actual solvable equations and comparison to. Gosh, I mean, it was, I looked at the publication of every lake that was similarly situated, where there was some data that could be put into the matrix to understand how Waiau fit in as a system. And I really do think it is a reflection of the geologic history and the fact that even though it is a highland environment, it's still pretty cool up there. And I think just the way everything is just situated, that with the sediment composition, that it just can hold the light.
Do you ever look at the other lake up there?
No, Waiau is an interesting I think because of where it was located, that people knew it was there. So there have been these visitations and so forth. And I was very interested in it too because it had such a deep cultural history, which what appealed to me because people cared a lot about it. It was very meaningful, and people cared very much that the lake continued to exist and the lake was basically able to sustain itself with a productive and healthy ecosystem that worked for it. So that was Waiau was my love for 3 years. I spent a lot of time trying to figure her out, and I figured I don't know everything about it, but what I did know about it was I was able to establish markers that could give us an understanding and a sense of where we are now and how things had been for such a long period of time that we could have a sense of what parameters were important to be mindful of, and that if something did change, that we could have some kind of understanding about what that change was and how it might be impactful, given what we understood about the interrelationship of some very significant variables to the system. Yes.
Do you know anything about those pipes that are hard to see, hard to miss?
I believe that they were part of Dr. Wilcox's pouring. My understanding was that when the lake was very low, that's when they realized that there was still evidence of that. I know from speaking with him that it was not an easy thing for him to get the cores. Basically he built a floating platform, and it's not like they brought in some big rig, and they had to manually do it. And I know that it took a lot of perseverance to accomplish the 7.5 meters that he did. So I think that was that failed. But to pull them back out would have probably been very difficult too, because you basically just have this floating plywood platform. So once he lost it and had to begin repouring, I think that was probably what's left behind. Yeah.
Would it be appropriate to cut it so that it wasn't this sort of, it has that sort of rubbish look of skew pipes,
Well, it's a thing. The thing about it is that I wasn't even so aware. I mean, it really does depend how obvious. When we were there collecting the contemporary sediments, and we're actually there was some people that dove to get those sediments. They didn't even mention it, and so I wasn't even aware until we were talking about the drought situation that there was remnants of that prior effort down there. It didn't seem to cause any disruption, at least to the ecological environment. So sometimes, if you try to remove things, you might create more disruption. It's a management issue. It's aesthetic, yeah. I don't believe that there's any ecological harm for that. Aesthetically. Yeah.
What's the diameter of the core samples that you saw?
They're not, they were like that, and yeah. So
I saw those pipes, and I could share my photographs of them with you, but that looks like about the inner diameter of the pipes that are still there.
I'm almost sure they were his, just because when he was allowing me to sample the materials and so forth, he constantly reminded me of how much trouble he had to go to get them, and I better darn well be very careful, and I should get as much data as I could from as little as possible, and that nothing left Hawaii. So any samples that I collected there from either his summary sediments, the contemporary sediments, water, anything, is still at UH. So that was very important, that the integrity of that data be retained at UH. Yes.
Did you ever notice any aquatic insects in sediment or just in the water?
Not in the sediment, but you wouldn't see that. You know, the reason the diatoms were there is because the silica was there. In terms of the insects, John Michalek, who was actually interested in the insects, he mentioned 2 things that he found. He published a paper about it. I think you mentioned today there was a couple things. When we were up there was with the beetle. Yeah. I'm not an entomologist. Yeah. See, I was sort of a misdirected biochemist. The diatom, you know, it ended up being such a useful tool, but it was the chemistry of the diatom that allowed me to really get to follow the history of it. It left a record that could be chemically analyzed, visually seen, because it still retained the frustral and the pattern. It was unique. Any other questions? What I've done is I had, you know, this is really funny too, is it's like, you know, everything's digital now. I had like several hundred slides, because we used to take slides. And I found somebody fortuitously that has now made them digital. So I've given them all to UH. I'm also going to be giving them a digital copy of my dissertation. This is something else that's funny, is that there's no internet, right? And no electronic publication. You have typed, and it was 50 cents a page, which was a king's ransom if you were a starving graduate student. And you couldn't use whiteout. You could only have, they would hold it up, and if there's more than 5 erasures and scrapings, the thing had to be retyped. So by the time it was done, you had to hand in 1 copy to be deposited with the University of Hawaii Library, and that was required for your doctorate. And I actually had a couple of other copies made and bound, and one I gave to my parents because I was the first person in my family to go to college, much less go on to graduate school. And my mom had died recently, and so I got the bound copy of the dissertation, which I'm also going to give to them because I'm very thankful for everything that University of Hawaii has done for me, and I'm going to look for the original data books for you as well. So hopefully we can continue to talk about Waiau, and anything I can do, I would be very honored to do that. Yes?
Is your intention to make them available to see digitally on the internet?
I don't know. I think you have a collection.
Yeah, I don't recall the older. I mean, UH distributes theses online. I don't think some of the old that they scan the older ones, but it's certainly available in the library if somebody wants to take a look at the thesis. And then there's a couple of journal articles.
Yeah, there was some journal. I caught 2 or 3 that came out of the research. So and you'll see, it was funny. I hadn't really realized. I never looked at how many times I was cited. But it's been cited a number of times, and mainly it was because of Starneus monacensis, the fact that the new species and the relevance of that to the biology of Hawaii, that there's a great interest in knowing what you have that is uniquely yours, is endemic to Hawaii, and understanding why it is unique to Hawaii. And I think that was the most interesting part of the question.
So yeah, our office has a online library, at least the database. If you go to omcam.org under Science and Library, you can search on all the research that's been published, whether it's about Lake Waiau or any other sort of Maunakea topic. You can at least reference it, and then from there we can help track down copies and things like that.
First, could you make those images available that the doctor had? She said hundreds of images.
Well, they're part of, you have lots of
Yeah, we can talk about that afterwards if you're interested.
Yeah.
So with that, Dr. Licata will be here for a few, but thank you everybody for coming tonight. We really appreciate it.